So more or less, these are the visible steps. But there is a password which is stored by one of the programs mentioned before, and the cryptographical algorithm is a kind of one-way mapping. So if you get your password from a database or DB table, then you should have some difficulties in order to restore the password. And in better places, some additional salt is mixed to the password so that it tries to slow down the opportunities for cracking it up. Checking password is very similar. The hash is compared with stored hash, and if they are identical, then a user may be logged in, and the hashing algorithm does not only determine by the cryptographical operation, but also cryptographical mapping and formatting beforehand. It has an importance, you will see through an example. Why cracking passwords? First of all, security audit is the main purpose for cracking a password. We would like to test if our users use safe passwords. And the other one is a kind of pen test, a kind of burglary test, when we get hold of the password of other users, and we would like to get some authorization with the cracking of other users' passwords. Then password crackers comes very handy. Either we load software down or we buy a proper password crackers. But what if we don't have any password cracker, which normally happens when the hashing algorithm is not known, no one has published it, no one has written a cracker. First example is a source code test, what is in the Apache Derby database. It's a very small DB manager written in Java. It can work in embedded client-server mode, and in client-server mode it can identify the user on the basis of the password. You can see the proper setting, and you can see that we started our Derby database server, which will just listen in port 1225, and then we use a client, and then we create a user whose name is test0, password test12, and then we ask for the new password. These are not standard SQL instructions, but this is how it works in the Derby. Password is a hexadecimal value not meant for human use. We would like to know about these values, so we load the source code, we look for the password text, and then we will generate this encrypt password function, or we will find this or search for this encrypt function. This is an SRA type of encryption. And before that, there is a conversion, a simple cycle or loop. All of the characters of the password is decomposed into upper 4 bits and lower 4 bits, and it stores it. And the loop is incremented after every step, but the cycle variable, the loop variable, is used in 2 instructions, one after the other, which will result in the following thing. Each and every character, with the exception of the last one, then the upper 4 bit of the previous lower 4 bit will be overwritten by the upper 4 bits, and you can see that we will lose data here as the bottom box overrides the top box. These are the consequences. ASCII code table is here in one column from capital A to capital O. We have the same upper 4 bits. So If anyone is given in the password, then we can see some examples of it. If a password consists of several characters or number of characters, then we don't only have 16 similar passwords, but several times 16 similar passwords with the generation of the same hash. And Derby will let us in together with the same type of user or the similar user. If so let's take 8-character password from lowercase, uppercase letters and numbers. And then the total number is 2 times 10 to the power of 14. The whole search in a video circuit board, which is relatively recent and quick enough, takes 21 days. And if we use the hex byte transformation in Derby, then it is drastically reduced to 0.23 seconds. Only 7 zeros must be written as the power of 10, and only 0.23 seconds is the time of total search. You can see that the ratio is 1 to 8 million. At least the computation need went down to this level or in this proportion. In May, the next version was released, which corrects this indexing error, and also an announcement was given with it, where they try to discourage us to use built-in authentication and not recommend it anymore. Instead of they recommend alternative versions, site-based database handling. Let's speak about reverse engineering. In the case of programs, we have 2 branches, one live analysis, the other branch is offline analysis. Debugger is the live and disassembler is the offline type, monitoring tools in the first case. If somebody knows these internal tools, then he will know that for the running of a program, we really can perform a real-time analysis or monitoring what kind of network operations is performed by the program. This is online live analysis. Offline uses a disassembler. So we use the eggs. We try to disassemble the eggs lines back to C code. It seems to be reliable and functioning well, but nobody has yet implemented it or prepared it. A database is a large, complex program. For example, in the case of site-based exa and DLL consists of several thousands of assembly statements or instructions, and it is not possible for us to check each and every assembler instruction because it is out of human scale. But instead, we would like to have a comprehensive picture of this, what a code section is doing with what purpose, and then I set up a theory about inputs, outputs functioning, which can also be seen from a debugger, and then this theory is tested, this hypothesis is tested, and if this hypothesis doesn't hold true, then I just search a little more in the code, modify it, and I keep repeating this cycle till I am proved right. Sitebase is a database handler for a large corporation. Market share fourth is in market share, in terms of market share, after Microsoft, Oracle, and IBM, and is closely related to the SQL server of Microsoft, because Microsoft bought its code in 1994 and started his own development. Password encryption, 2 types of algorithms, CPROP and SHA-256. The first is our own development. It is not officially published. The second is officially published. Now the later one, the latter one is the newer one, or the most recent one. First, let me speak about SHE256 hash, how it operates, how it functions. First, I start a site-based database from Windows or a simple command line, and I step in, I enter, look for login password, and this is the algorithm which authenticates it or delimits it. I ask for the password from the table, the appropriate table, and there are these long sequence of bytes. Always start with a constant, C007, and the rest of the number of bytes is identical with the output +8, which will be SAL, if I understood it correctly, speaking extremely fast. Let's check how it works. We should find entry points to the program where we can catch that part of code segment where the conversion takes place. We can find the system calls, or look for system calls, input output, writing out inputs and outputs, or network file operations. For example, in the case of a cryptographic algorithm, is looking for known constants in order to find the entry point. And then we will check the description of Sybase in the algorithm. It is a simple conversion of the password, 16-bit conversion. And then sort is just added to the result or a link to the result. And no matter how we try to reproduce it, it will never come out what is actually being stored in the database. If we take a look at the description of this algorithm SHA, then lots of constant numbers, constants can be identified, because the algorithm in its last steps uses these numbers. And on the screen we can see the memory space for one constant. We load in our debugger, start it, and then we just jump to the process of the operating system which runs the database handler. And because of the peculiar feature of the interprocessors, bytes appear in reverse order as opposed to the scripted ones. So everything happens within 4 bytes. This is the conversion or the reversing. And then this is a constant, and we will also find many other constants, but this is our useful constant. We set a memory breakpoint to the debugger. So the application wants to access these bytes, and the debugger will stop and shows us how far it has gone. This is the memory breakpoint. We change the password for a user, and the database handler must carry out an encryption or hashing, and these are the last steps of the 256. We know that it was an HL256. We have a stack called stack function. Debugger will try to restore on the basis of the stack values and those function calls that happened before. These are the list of the embedded function calls, and one of these calls uses or contains our password as a parameter. The next step is to find the instruction which calls this function, and here we put an instruction breakpoint in, or insert a breakpoint. And if we inserted this breakpoint and the program has stopped, then debugging is going on stepwise, and there is a call. These are our converted password, lots of zeros and then 8 bytes at the end. This is the sort, because when we inquire about the passwords from the database, then next to the encrypted hash we will find these 8 bytes. If we just count the number of 0, then we will exactly know how long it is, what its length is. And then we can check our hypothesis, and then where we get is the fact that hash will also be found in the database, so our reconstruction was right. These are the details for security's sake. And then with Laszlo Tóth, my colleague, we developed a cracker under a relatively short time, and then OpenSSL is the library or the directory code where you can find. And there was some replacement here and some modification of the encryption and hash algorithm. This can be downloaded from this homepage. Good.
Well, from now on, we'll take a bigger bite into the reverse engineering of this unknown algorithm. And we need to know, and this is a stumbling block. The old Sybase version is not available, and the current version is not supportive of this, no longer allows for CPROP. I understand that Sybase 12 is still being used, and it supports this algorithm, so it still is of practical use. Well, for the last time, it was 12.01 where this was of use, and all we can download on a trial basis is 0.5. If we study the documentation, you will find that downgrading is possible, setting back the database release from 15.0 to 15.01, and we can have access to the old type password encryption. And now we'll do the functions that are missing from the screen. And now if we log in using the user information, the login password parameters, the old algorithm is next to the new algorithm. And if we check the password encryptions, we will find the old encrypted and the new encrypted versions side by side. And they are pretty similar when you look at the endings of 256, and the byte number is the same, so it's probably the same. And that's the old password encryption hash. In the second byte segments, you will find 0.5. It's a similarity. So we try to analyze what's going on. We start debugging the old password encryption algorithm, and there's a function call. The output is 64 bytes, and the last 28 bytes is included in the old hash in the database. Now we get inside this, and we have a notion that it's block cipher, but it's not DES, not AES. No specific constants are found, and we must come up with a way of identifying it. When we've run out of possibilities, we get IDA-free That's the IDA assembler will establish that the symbol tables are linked to the database manager code, which means IDA can restore the function and source names. until IDA parses these exe files. What I did using my virtual machine, I waited an hour. It wasn't anywhere in the process. I went to bed, went to sleep, and in the morning it had cracked the parsing information. And the assembly code has this solution here in the meta encrypt line. And the meta key SCH call is going to provide an output that becomes the input here. So meta key SCH in some way participates in the generation of the encrypted hash. And after some investigations, we find this logic. Here you get the details. Meta key ESC gets a password, produces an output of 64 bytes. Meta encrypt produces another 64 bytes, and the last 8 bytes will be the encrypted password. And now we need to crack these boxes. Meta encrypt first gave us these clues, and these are the simpler things, about 80 assembly instructions. There are 5 function calls, so it's not only 80 instructions, but there are calls embedded, and there are further embedded calls. And about conditional jumps, we have approximately 7. Now we look at the backward engineered assembly code. We notice 2 things. First, here's an interesting 4-letter acronym, FEOL. That's a block encryption algorithm. Those of you knowledgeable about encryption will know this, and it's not really used anymore. And also, there is a constant string, a const string, which is the input for the encryption. Now, let me say a few words about FEAL. It goes back to 87. It was a replacement for the DES algorithm, just as secure but faster to compute. It's based on Feistel networks, and there's a key scheduling portion followed by the encryption-decryption phase. There is lots of different alternatives which vary as to the number of key size and also the cycle numbers. The algorithm cycles, that is, and the X is the latest version. Vulnerabilities were always uncovered in the last one. Whenever a new one was published, another vulnerability was always exposed, and they got fed up with it, and they made it not recommended for use. Now, which FEOL version is in Sybase? I try to give you a brief summary. I mentioned that there's a key schedule size which produces subkeys for the internal encryption cycles. Depending on which release we are using, the number of internal cycles will be different. So the key scheduler's output is going to be different because the number of cycles will be different as well. So FEOL 8 has 38 such cycles and bytes, and that's a clear indication that we're talking about FEOL 8 as the algorithm here. And that's the string constant here, 8 blocks worth of data, 8 times 8 bytes, and that's a riddle. I will spare the audience all assembly descriptions, but working backwards in the code, you must see that each internal cycles uses the constant string, one of the blocks, as input, and it ciphers those. So there's a special block which will use the meta keys function output, and that's what is generating the encrypted output. And that's very much like the Sybase solution. One difference is that there's no initialization vector, and in each cycle a different key is used, whereas Cyblock chain uses a different one in each cycle. And now we'll get complicated. The meta key SCH is a key scheduling algorithm. It's more complex. It consists of 450 assembly instructions, 15 function calls, and 29 conditional jumps. Looking inside, you will see that in each cycle it produces what we call salt, 1 byte of random value, and this 1 byte is used here. And it's mixed using XORs to the input of the next cycle. It also indexes the input and output. But here's a simple chart. Take this 1 byte, that's the result of the random call. It returns 1 byte. And you XOR that with each byte of the input. You change it in some way. And the weird thing is that after the second byte is that each next byte is going to get the next XOR result. And again, I'll spare you the assembly instructions walkthrough. Here's an overview. 8 rounds. There's some form of initialization. Step number 1 is that the password is enhanced to 57 bytes. It's a weird combination because it's not even an even number. And at the beginning, it will initialize the seed number using the system time, from which it generates a single byte, and it hands it over to the srand function. With the rand call, there's a round salt byte. And again, here's a process chart to give you a better idea. We take the expanded password, 57 bytes, and in this case it starts with byte 0, and in this case we check the first 8 bytes. We need to note that here's the random value of 1 byte, which is mixed into the input. And it's important to see that encryption only takes place in the first 2 rounds, and it takes the seed number to calculate one of the positions. Security by obscurity was achieved through combination, because they thought that this is so complex that nobody is going to make any sense of it. And the mixing is going to alter the outcome of each round. Now we can implement the algorithm in C. Field 8 can be implemented using applied cryptography by Bruce Schneier. I checked 4 or 5 sources, and that's the one I could have an overview of the most easily. C source code can be found at this useful link. And each step can be reconstructed precisely. And something is still wrong, because the output is not correspondent to the password stored hash code, which means Sybase in some way uses not quite the official field 8. Digging deeper in Sybase, we will see that different from the official implementation, the key schedule is only the first 4 bytes, and the other bytes do not match. So something different is taking place. We'll start to analyze how this is working precisely. Here's the mathematical definition. One variable, which is used in all the rounds, that is initialized with a value of 0, and it's updated in each round, and Sybase forgot to do that. It seems a complicated definition, but at the source code level, it's a single instruction. This is the one we need to skip in our own implementation. So, in summary, let's check out the structure of the hash. The first byte, which we decrypted, will give us the initialization of the random number generator, and the sort number will become the same if the seed number is the same, because we're only using one quasi-random generator, so it's not a true randomization. And the hash type indicator can also be 6 or 7. I saw on the internet certain versions in which there was 1 or 2. It must have been based on DES, so I couldn't use that for anything. I discarded it. And the last 28 bytes gives you the hash of the meta-encrypt result. So I've successfully backward engineered this code, and it's not been published, although I've heard that some security experts have this. So how do we crack our own password? All passwords operate in the following way. In some way, we'll have to produce TES passwords and format them using salt, and then generate the hash using cryptographic transformations. And if the password hash matches the hash to be cracked, that means it's the same as the original password of the user. How do we produce the TES passwords? One is to use a word list or brute force. You've all heard of this. There are two approaches. First, use intelligence to generate the password connected with the user data. As Alex and I spoke about this yesterday, he thinks that the more we crack passwords, the intelligent approach seems to be more conducive. And the Markov chain approach is the other interesting one. Take the words in the Hungarian language, and we collect statistics on consonants and vowels and their relative frequency. And also certain vowels followed by certain consonants. There are patterns, and probabilities can be assigned. So we can generate patterns which correspond to the statistics, and that's an interesting approach. Now, as to functionality of a password cracker, we don't just crack one single hash. In a security audit, we crack hundreds of passwords in parallel, so you must be able to process multiple passwords simultaneously. Not all crackers can do that. The other key feature is session handling. That means if we pause the process for whatever reason, because we want to use the machine for a different purpose, we don't want to use up all the resources, and then we can pause it and we can carry on where we left off. Well, these are the key prerequisites for being a good password cracker. How can we speed up the password cracking process? Method number 1 is all modern 86-based CPUs will include parallel execution units. We take an instruction and implement it using several bits of data. So the data pool will give us a chance to multiply execution speed. And of course, special instructions must be used. And that's one opportunity. The other one is to use the GPU, the graphic processor unit. The main difference is that the parallel units are not using instructions, but the kernel which is uploaded to the video card using separate threads. In the execution unit, there will be branching processes, and different codes may result from this. And that means it's not certain that the same steps take place at the same time. What makes this difficult is that if you take a GPU, there are lots of executable units, but if we want to write fast code, we need to use the shared memory or the registers of the CPU, and they're both a limited resource because the shared memory is 16 to 32 kilobytes, and the register is even smaller. That's about the equivalent of 8 kilobytes. Even that is shared across the execution units, so they will have less and less memory as their numbers grow, which is quite a tricky thing. Just to give you a sense of how this goes, well, the top of the range cards and cutting-edge GPUs can have up to 500 or 600 execution units. Just to give you an estimate of the performance gain relative to CPU processing, modern CPUs rely on multiple cores. So in addition to the parallel opportunities, they have several cores which you can separately use. So 3 to 10 times faster is how much faster you can get. Of course, that depends on the GPU and what you use the video cards for and how you code all that, so the speed gain is not automatic due to the above-mentioned factors. I actually wrote one of these password crackers on GPUs. NVIDIA and MySQL and Oracle 11 hashes are used to crack passwords simultaneously. The features include the ability to process several password hashes at the same time, and they also handle session handling. That, of course, means that password cracking is going to burden the GPU so much that it just about goes dead and you can hardly use it for any other operations. And of course, I'm not getting into the details. It's a lengthy process to develop one of these. It's one thing to write the code and use the GPU, but it's another thing to make it work effectively. And proprietary hardware, special integrated circuits can be used. While the fastest computation performance, to the best of our knowledge, is achievable using the ASIC chips, where the transistors are fixed and burnt, so they only handle a single process. You can't program that. And if you want one of these produced, it takes a lot of startup capital. Several millions of dollars. That's one of the options. FPGA is the other option. That is, transistors can be programmed. This is used for circuit simulation. And of course, you can perform any operations. You can use them for computing as well. What you need to do is know that FPGA is 4 to 5 times slower than hardware implementation. I heard this in Krakow at the conference called Confidence, and I spoke to a colleague from the US producing proprietary hardware for cracking passwords.
This is my personal opinion on the possible speed-ups. If we had a special purpose hardware, then we can make it faster. It depends on who would do this implementation of this high-base algorithm. The other thing that I'm missing here is that I've never heard of special purpose hardware which could delete or search several passwords parallelly. And as conclusion, any kind of hashing algorithm can be reverse engineered. Security by obscurity is absolutely useless. We cannot hide these things. And on the surface we can find lots of source code which will help us in development, and we shouldn't start from scratch. Every technology has some advantages and disadvantages. If we have a special purpose hardware, we may use brute forcing. If we would like to delete passwords within the framework of an audit, then even a simple CPU is useful. Thank you for your attention. So much about my presentation.